Okay, so welcome everybody to our Monday seminar. Today we are very happy to have with us Professor Simon Catterall from Syracuse University. Remember that as usual, we ask you to stay muted if possible, and if you want to ask a question, you just unmute yourself. There will be also a version of the talk recorded, posted on the YouTube channel probably by tomorrow. So without much ado, I will just leave you with Simon, who is going to tell us about how to put n=4 super-Young-Mills theory on the lattice. Thank you.
Thank you, Jose, and thank you to the organizers in general for giving me the opportunity to chat to you about supersymmetric lattice constructions. So I'm going to review work that's been ongoing for more than a decade now to put supersymmetric theories on lattices. But I'm going to focus particularly on n=4 super-Young-Mills, and towards the end of the talk, I'll even have time to tell you about some recent numerical results at very strong coupling, which look kind of intriguing. All right, so let me move on. And now, oh yeah. Okay, so here's an outline of my talk. So I'm going to briefly give you a review of some of the motivations and difficulties associated with constructing supersymmetric lattice theories. And then I'll focus in on the most important key idea, which is that if one tries to do this in a way which preserves some supersymmetry, it's important that you pick a starting point which doesn't correspond to the usual formulation of Young-Mills theories, but a sort of topologically twisted version of those theories. And I'll explain that in some detail, and that's a much more convenient starting point from the point of view of latticization. I'll give some specific details for n=4 Young-Mills. And then I'll spend a little bit of time talking about some of the residual issues that arise once one comes up with one of these constructions. So there are issues about sign problems potentially, instabilities associated with the flat directions you expect in a super Young-Mills theory. And then there are additional problems potentially coming from a strongly coupled U1 sector of the theory that you have to incorporate in the lattice, which you don't ultimately, you're not interested in the long run, but can cause you problems if you're not careful. And one of the take-homes from this talk is that we've recently, we think, solved that problem finally, at least in the case of SU2. And that allows us finally to get out to very strong coupling. And so I'll spend a bit of time talking about some recent results in a paper that was on the archive in the last month or so on supersymmetric Wilson loops, which have just been rendered possible by this these recent improvements to deal with the U1 sector. Okay, so this is work that's been done in collaboration with a large number of people. I think I've got most of the names here. I will highlight Goksu Kantoga, who's my current graduate student, who's responsible for most of the recent numerical results you'll see towards the end of the talk. All right, okay. So let me just give you a brief motivation for lattice supersymmetry. Of course, supersymmetric theories have been interesting for a long time as toy models for things like chiral symmetry breaking and confinement. More recently, of course, there's a lot of interest in the supersymmetric gauge theories from the point of view of revealing, giving explicit examples of dualities, of conformal field theories, and of course, holographic connections to holography. And so there's a lot of interest in trying to put these things on lattices because many of these interesting features arise at strong coupling. So it would be a natural thing to construct a lattice theory and allow you to simulate it numerically. And so that's obviously the main motivation for what we're doing. Of course, the reason most people aren't doing this in the lattice community is that, and traditionally haven't for many decades now, is because it was appreciated very early on in lattice gauge theory that supersymmetric theories are particularly difficult to put on lattices because the discrete space-time itself breaks the supersymmetry algebra at the classical level. So just from the fact that the supercharge is anti-commute to give P, the generator of infinitesimal translations, it's immediately obvious that since once you go to a lattice, you no longer have infinitesimal translations, you're going to break that algebra right up front. And you can see this in many other ways. If you try to take a naive discretization of a supersymmetric action, then the manipulations you need to show its supersymmetric invariance involve recasting terms as total derivatives and things like that. And since the Leibniz rule doesn't hold for discrete difference operators, that's how the thing manifests itself concretely. You're just not able to guarantee supersymmetric invariance typically in a sort of a naive latticization of a supersymmetric theory. So that leads to lots of fine tuning to restore supersymmetry in the continuum limit, especially if you have scalar fields in the theory. And so that's been a barrier to constructing and studying supersymmetric theories for many, many years. And the realization, which is more than a decade old at this point, 15 years probably, the solution to this is to try to preserve some subset of supersymmetry, the SUSY algebra when you go to the lattice, all right? And then you hope that that subset of the SUSY algebra will help protect you against some of these dangerous kind of radiative counterterms that are induced when you associated with the supersymmetry breaking. So there are many examples of these kinds of constructions that I'm going to tell you about today in dimensions less than 4. But in d equals 4, it seems like there's just a single unique solution to all of these different constraints, requiring gauge invariance to be preserved, requiring some supersymmetry to be preserved. There seems to be a unique solution to those constraints. And it turns out to be n equals 4 super Young-Mills. So that's what I'm going to focus in. And of course, that's probably one of the most interesting supersymmetric theories from the perspective of things like holography anyway. All right. So of course, n equals 4 is a particularly interesting theory. It has this conformal phase, which is what we'll be focused on today. There are all these connections between gravity and anti-de Sitter space and n equals 4 on the boundary, the original ADS CFT correspondence. It's thought to possess this property of S duality. It's a testing ground for reformulations of scattering amplitudes. There has been some interesting work also in the conformal bootstrap program connected to n equals 4. So there are lots and lots of reasons why n equals 4 is a lattice realization of n equals 4 will be a very useful thing to have. Just briefly, I'm sure most people are aware of this. So it's an SUN gauge theory. It has 4 Majorana fermions and 6 scalars. They're all massless and in the adjoint representation of the gauge group. And you have an action consisting of kinetic, Yukawa, and 4 scalar terms with coefficients that are all related by the n equals 4 supersymmetry. So in terms of supercharges, there are 16 real supercharges in the game. And both the fields and the supercharges transform under a global SU4 or SO6 R symmetry. So those are all the features that have to be incorporated in any lattice construction we come up with. All right, so what is particularly special about n equals 4 from our perspective is that the global symmetries of the theory admit what's called a twisted rotation group. So the usual theory, I'm in Euclidean space, the usual symmetries of the theory correspond to a Lorentz symmetry, SO4. And then I can pull out an SO4 subgroup of the R symmetry. And I can imagine decomposing all my fields under a sort of diagonal subgroup of these two symmetries. Okay, so what that means in practice is that the fermions, which carry in a spinor index alpha, say, and an isospin index, a flavor index I, they transform by Lorentz transformations L and by these R symmetry transformations R in this way. And if I just focus on the diagonal subgroup of those symmetries, so I basically set R equal to L, then you can think of the fermions as basically transforming like a matrix under this subgroup of the symmetries. Once you have, say, a 4x4 matrix like this, you can imagine expanding it out on products of gamma matrices. That's a perfectly good basis for a 4x4 matrix. And then these objects that are coefficients in that expansion are basically antisymmetric tensors, p-forms. All right. So the reason n equals 4, the reason we can make any progress going to the lattice with n equals 4 is precisely because it admits this expansion, where I remove, if you want, the spinor degrees of freedom and replace them by antisymmetric tensors. And that's rather nice from a lattice perspective, because it's always problematic how to deal with spinor fields on a lattice, but you actually have a good idea what you should do for antisymmetric tensor fields. You can naturally associate antisymmetric tensor fields with things like links and plaquettes and higher dimensional objects, simplices in the lattice. So there's a very natural place to put these antisymmetric tensors representing the fermions, and that's sort of one of the keys that allows you to discretize the theory. You'll see in a moment that in fact we actually repackage this expansion in terms of sort of a 5-dimensional language. So we're going to expand not on the original gamma matrices, but on these guys where if you want to, it looks like we're living in 5 dimensions. We're using the 5 gamma matrices, including gamma 5, to expand on, and then we're just going to take all the other ones to be proportional to this gamma A, gamma B. So these indices run from 1 to 5. All right, so this is just a repackaging of the original expansion that we would write down naturally corresponding to this diagonal subgroup. And you'll see in a moment, it's actually allows you to write the action in a very a compact way in the continuum. Essentially, it's the dimensional reduction of a 5-dimensional theory.
Question?
Yeah, sure.
You have to make a choice of SO4 subgroup.
Yes, that's right.
Is this going to lead you to trouble in restoring the SO6 in the lattice later?
So when you that means that some of your scalars will some will transform as vectors and some will transform as scalars under this decomposition, right? And so, but you'll see when we construct the lattice theory, in fact, we actually do something closer to decomposing under a diagonal subgroup of SO5 cross SO5. So in fact, we'll end up with objects, as I've shown you for the fermions, where the indices run from 1 to 5. And that's naturally associated with a particular lattice in 4 dimensions with 5 basis vectors. So when we come to the lattice construction, I'll be showing you something slightly different from what I've written down, right? So you can get to this theory by then just doing another dimensional reduction in the continuum of from 5 down to 4 dimensions. So that's what we'll be using. I don't know whether that answers your question. Maybe it'll be clear when we get to the actual lattice construction. So some of the scalars, you know, all the scalars get packaged up as if you want, as part of gauge links in the end. And so there's no ambiguity, there's no choice needed when you come to construct the lattice theory. It's sort of unique. Yeah, should I just move on?
Sure, okay.
So as I say that in the bottom here, the 5-dimensional language is kind of will turn out to be very convenient for the lattice. And in fact, it even allows you to write down the action even in the continuum for n equals 4 in a very compact way. I'll show you that in a moment. So we're going to essentially arrive at n equals 4 Young-Mills by a dimensional reduction of n equals 2 Young-Mills in 5 dimensions. And if we do that in a particular way, we can write down a 4-dimensional lattice theory very nicely. And the action is extremely simple. All right, but it's important to realize this is just a relabeling of variables at the moment, right? I'm not changing the fundamental symmetry group of the continuum theory. I'm just decomposing all the fields under this diagonal subgroup. Okay, so the fermions are now recast as tensors, antisymmetric tensors. What about the bosons? Well, the gauge fields are singlets under the R symmetry, so they're going to remain vectors under this twisted symmetry. The scalars are also vectors under the R symmetry, so they become vectors under the twisted symmetry. So one of the features you immediately see is that the scalar fields of the theory, or at least some of them, end up being associated with objects with integer spin under the twisted group. All right. And in fact, what happens is the bosons in the twisted theory can basically reappear as complex gauge fields. So you'll see when I write down the action in a moment that this formulation of n equals 4 is written entirely in terms of these complexified gauge fields, which are built, and there are exactly 10 real fields packaged here. So that corresponds to the 4 gauge fields and 6 scalars of the original theory. You've had 10 bosons in the game. There are 10 bosons packaged up in these curly A's, these calligraphic A's. So the scalar fields basically are playing the role of B. Well, 4 of them are going to be the 5th gauge field, if you want, corresponds to the 2 additional scalar fields in the theory. So 4 of them gauged into from the other 2 remaining scalars. Can you hear me okay?
There was a little bit of a...
Yeah, I just got a little message saying internet connection unstable, but hopefully it was just a one-time glitch.
If you have
so everything in the action.
If you have trouble, you can try sharing only the PDF or the
right. Well, hopefully we won't. But if worst case, I send you the slides so we can just move to those in worst case. All right, so you'll see in a moment that the action can be written entirely in terms of this sort of complexified field strength, just the commutator of two covariant derivatives built out of this complex A, right? And so you can decompose it into its real and imaginary parts if you want to. So this will all become a little bit clearer in a moment when we move on. Are there any more questions about this before I? Okay. All right, so originally we had these 16 supercharges. If I repackage them in terms of these, like the fermions, then I'll end up with a scalar, a vector, and this antisymmetric tensor, right? So there's a 1, a 5, and 10 of these guys that make up the 16 supercharges of the original theory. And all of these act on the fields in particular ways, but the one I'm most concerned about is the scalar supercharge. That's the one I'm going to be able to put on the lattice. All right, and so that acts on these fields in a particularly simple way. So it just takes the complex boson into one of these fermions, psi A, we wrote down before. Psi A itself is a singlet under Q. It takes the fermion chi AB, those 10 fields, into essentially the dagger of the complex field strength. And the scalar fermion goes into a scalar boson, which is basically an auxiliary field. So that's a singlet under Q as well. And A bar as well is also a singlet under Q. So we introduce this extra bosonic field just so that the equations of motion, so that symmetry remains basically nilpotent off shell. So it's very easy to see that Q squared is 0 in any of the fields. And this is the heart of why you can port this thing onto the lattice. Before we basically had Q squared was P, and P was a problem. Now we just have Q squared of 0. So of course, there's no immediate conflict with the latticization at this point, all right? Because the right-hand side is clearly, no longer has P involved, all right? So this looks like a BRST charge, and there is a very interesting story about how you can construct this theory by a process of gauge fixing from a simpler bosonic theory. We don't need that for this talk, so I'm not going to say anything more about it. But if you think this looks like a BRST charge, you're correct, and there is a way in which this theory can be, quotes, derived by building up from an underlying bosonic theory of these complex gauge fields A with a topological shift symmetry. And once you do that, then you would interpret these psi's and chi's as ghosts, basically, in that language. But I won't have much more to say about that right now. So here's the action that we need, and we're still in the continuum right now. So I can obtain the usual, well, the twisted n equals 4 action that I want. This is actually the Marcus or geometric Langlands twist, the 3 twists of n equals 4 Young-Mills. The one that works from the perspective of constructing a lattice theory, the one I'm talking about, was originally constructed in the mid-90s by Marcus, and then it was repurposed as part of the geometric Langlands program by Witten and other people, Capison, I think, later than that. So this is what we're using, and you can rewrite that action as essentially a dimensional reduction from 5 dimensions of this particular object. So it's a Q variation of something. So again, there has this topological flavor to it. That something is chi dotted into F, A to the scalar fermion onto d bar D, and then this piece involving the auxiliary term, all right? And then you have to add to that a unique extra. So this is clearly Q invariant. This is clearly supersymmetric because Q squared is 0. There's an additional Q closed term that you need to get back to n equals 4, which is sort of, again, naturally lives in 5 dimensions and just corresponds to contracting 2 of these chi's with the d bar and then the epsilon tensor. Right. So you can show, but just by naive dimensional reduction, that this thing gives me the Marcus twist of n equals 4, right? And in fact, from our perspective, this is closer to what we actually put on the lattice. All right. So it's obvious, by the way, that the first term is supersymmetric. It's less obvious where the supersymmetry of this term comes from. It just comes because when I act on the Q closed term, I turn one of these chi's into an F bar, and then you have epsilon d bar F bar, so it vanishes by the Bianchi identity. And remarkably, that property will survive in the lattice construction I'm going to show you as well. So the first term, it's sort of natural to imagine that if I put this on the lattice, I can be supersymmetric because it's Q on something, and as long, it doesn't really matter what the something is, it will be supersymmetric, because if I can maintain Q squared of 0 on the lattice fields, then the first term will automatically be supersymmetric. The second term, it's more surprising, but it will also turn out to be true. Now, in flat space, you should think of this as an exotic change of variables, right? You've focused in on a particular subgroup of the global symmetries. You've rewritten the theory in terms of variables that are sort of natural in that language. But at the end of the day, this full symmetry theory is what it was before. You have an SU in the continuum. You have an SU4 R symmetry. You have ordinary low-end symmetry, et cetera, et cetera. It's just you're rewriting in a language where some of that is obscured. So in flat space, this twisted formulation is identical. The content is identical to the conventional one. All right. It would not be true once I go to a curved space, because clearly when I represent fermions by tensors, I'm changing the coupling to gravity, for example. So it's certainly not true in curved space, but in flat space, that's the idea. So it's a perfectly reasonable choice to make. It's just going to be a much better one from the point of view of discretization, principally because you've exposed this scalar fermion and this scalar supercharge, and those are the ones that end up being possible to preserve when you go to a lattice. Okay. Another point to sort of emphasize at this stage is the fact that although I'm using this language of topological field theory and writing a formulation that would be natural for the construction of topological field theories, this is not a topological theory. The topological constraint that Q has to annihilate the physical states is not incorporated here. That would just get me to the ground state of the action. And I'm thinking this in a much more general terms. All right, so I'm not restricting myself just to focus on the ground states of the theory. I'm allowing this to be just a general change of variables. Now, the fact it contains this topological subsector is actually very interesting and super useful from when you get to the lattice, because it means there's a sector of the theory you can compute exactly. And you can, if you want, test your simulations by making sure you get those answers right. All right, so there is this topological sector, and we will use it, and I'll show you some interesting things that come from that. But you should think of this as just a strange change of variables at some level in the original n=4 action, but one which is more suitable for sort of lattice discretization and will conserve some element of supersymmetry when we go to the lattice. By the way, feel free to stop me anytime. I don't have that many slides, so we have plenty of time for questions, and it's best if you ask them as we go along rather than leaving them all to the end and things like that. So if there's any questions now, please pipe up. Otherwise, I'll just move on.
I have one.
Sure.
So you realize exactly the Q symmetry on the lattice, but there is still more supersymmetry to realize.
Correct. Right. All the other
does it come as an accidental symmetry? I mean, are you able to cancel all the relevant and?
So I'm going to say something about that later, but the essence is if you can preserve some supersymmetry, the hope is it eliminates a certain number of relevant counterterms that could be induced through quantum corrections, because certainly you break the other supercharges when you go to finite lattice spacing. And so it turns out to be the one supercharge is actually pretty constraining. There's basically one marginal operator you can write down at the end of the day, which is incompatible, which is allowed by the Q symmetry, but would be forbidden in n=4. And so there's one operator you may have to tune the coefficient to take the continuum limit and get back to full supersymmetry. So it's almost good enough. So 1 out of 16 supercharges turns out to already be a lot. It's not so surprising. Most of the cancellations that go on in supersymmetry just depend on having, one fermion state for every boson state, and a single supercharge already gets you that much. And we'll see the requirements of lattice gauge invariance are also very restrictive, and so that cuts down the counterterm structure too. So it's certainly true that we're preserving only a small fraction of the supersymmetry, 1/16, but it turns out to be already quite a lot, it seems. And I'll show you some sort of numerical evidence, but we can also make, analytic arguments about that, and I will do that in a short while.
Okay.
Yeah. So just to give you a bit more detail about what the lattice action looks like. So there is a bosonic piece and a fermionic piece. To get this, you go back here, take the Q variation of this. This gives you chi goes into F bar, so I'll get an FF bar out of that term. When I do the Q variation on here, I'll get a d psi, so I'll get a chi d psi term, and then there'll be other pieces coming in from this as well. So I get, here's my FF bar. This is just coming from the square of the auxiliary field, so there's a d bar d term. All right, so I'm still in 5 dimensions at the moment. just formally. And then the Q closed term is living here, and here are the fermionic pieces coming from the first term. All right. So if I've just done the Q variation and integrated out the D field basically, and this is what I get. All right. And then if I do a naive dimensional reduction on this down to 4 dimensions, and then decompose these fields under that SO4 subgroup, then I'll find the Marcus twist of n equals 4. All right. So you can sort of see that this, if you just go back to this formulation, this is actually a very compact way of writing down the action for n equals 4 super Yang-Mills, just in the continuum. And it turns out to be essentially the starting point for the lattice construction too. All right. So, okay, so everything I've said so far is on the lattice, and now I need to, in the continuum. So now I want to go to the lattice. So as I said before, the fact you have sort of geometrized the fermions is actually quite useful from the perspective of constructing a lattice formulation, because you already know roughly where all these fields have to live. So this scalar fermion has to just live on the lattice side. It has no option. It's the natural place to put a 0, 4. Something like psi A has to live on a link. So you're looking at lattices which have parameterized by some basis vectors, which run from 1 to 5. So there'll be 5 of these psis. That's the reason we're using this sort of 5-dimensional language. And the chi's basically run on, they're associated with plaquettes, but I can think of those plaquettes as additional face links, which run from x plus a plus b to x. So we sort of immediately know where to put the fermions just from the fact that they are antisymmetric tensors. There's a well-known mapping of these continuum antisymmetric fields onto the lattice. So the gauge fields would naturally also live on links, just like they would in QCD, right? And in fact, you can see that they should live on exactly the same links as the fermions, because Q takes a curly A into an psi. So if you want your supersymmetry to be compatible with lattice gauge invariance, right, then you should place the A's should live on the same link as the psis with the same orientation. All right, so that's very natural. So if you want, you would have done this to start with, and now you learn that psi has to be on the same link just because of supersymmetry. I need a prescription for replacing continuum covariant derivatives by some sort of finite difference operator. And so there is a natural prescription for doing this. And here's what I would use for dA psi. So what it is in general, these things look like sort of generalized commutators of the gauge field, this complex gauge field with the fermion. You can immediately see if I take U as 1 plus A, so I look at the naive continuum limit, you'll find here there will be a piece that looks like psi b x plus a minus psi b. So that's the forward difference operator.
Sorry,
and then there'll be sorry.
Can I ask a question?
Sure.
These fields are not in the group, right?
Correct.
They're just in the Lie algebra.
Everything is in the algebra. So this is very different from QCD. I'm going to have to handle gauge fields in the algebra.
Okay, thank you. That's what I thought.
Again, it's required by supersymmetry. If the fermions live in the algebra, then the lattice gauge fields must also live in the algebra. Otherwise, you would break supersymmetry at the level of the Q transformation.
Okay, thanks very much.
Yeah, I'll say more about that in a little bit. Yeah. So it's not hard to convince yourself. This prescription I just gave you actually gives you basically the continuum covariant derivative leading approximation. If I just put the U as 1 plus A, I get a derivative operator and then a commutator of A with psi, which is the correct covariant derivative in the adjoint representation. So it certainly has the right naive continuum limit. You'll notice both terms transform as sort of Wilson lines between X and X plus A plus B. Both of these terms have that property. And that's crucial. So this has this transforms covariantly under gauge transformations. In fact, it transforms like a line from X equals from X to X plus A plus B. Both terms fit like that. That's very important because I have to, if you go back to the action we just looked at, wherever it is here, I have to contract this derivative basically with a chi AB. And now you understand why I put the chi ABs on these extra face links. This is the wrong way around. Okay. So what happens is this looks like a path from X to X plus A plus B. I'm going to contract it with something which also runs from it should say x plus a plus b down to x. So the orientation is wrong on this. It should be x plus a plus b down to x. Okay, but anyway, what you can see is this forms in a closed loop. All right, so formally, this prescription for derivatives allows me to write down terms which look like the continuum terms, but are lattice gauge invariant. They are lattice closed loops. All right, so that's absolutely crucial. So the derivative is like a link going from x to a plus b, and the chi's should read x plus a plus b down to x. So they have the opposite orientation. Right. So this was the correct orientation. This one is incorrect, sorry, on the slide. All right, so now it turns out that this prescription of writing basically derivatives as generalized commutators with the lattice fields so that you get consistent link paths generalizes to arbitrary p-forms. I won't give all the results here, but there's a sort of technology for replacing all these derivative operators in the continuum by appropriate sort of shifted commutators such that they have the right naive continuum limit and such that they will generate closed link paths when you contract them with the appropriate fields in the lattice action. So you can maintain lattice gauge invariance, but now, you know, your fermions are mostly living on links now, not on sites. So it's, again, very different from lattice QCD, but it's sort of forced on you by this geometrical sort of discretization, this geometrical formulation. Right, are there any more questions about that? Right, because this is sort of a key element which differs from the continuum, but it's very close to it in spirit. Right. By the way, these formulations were originally written down in the 80s, these derivatives, in an obscure paper by Ratin and collaborators, where they were thinking about supersymmetry, but they didn't know about twisting at that point. So they were just trying to write down derivatives in adjoint representation for gauge fields. Of course, their constructions didn't really make sense because they weren't really in the algebra. But again, most of the rules come from that old work that sort of was disappeared and was forgotten about. But it turns out to be perfect for these constructions. I should at this point also add that these formulations I'm telling you about were originally written down by David Kaplan and Mithat Unsul and people like that in the context of orbifold constructions. So you can generate exactly the same Yang-Mills lattice actions, supersymmetric Yang-Mills lattice actions using orbifold and deconstruction techniques. And these derivatives come out automatically from those constructions. So it's kind of rather remarkable that you end up in the same place. I think the twisted picture is actually simpler to explain and more powerful in many respects, but it's equivalent to the orbifold methods too. So,
but then the fact that you have fields in the algebra means that you have homogeneous terms in the gauge transformations? Or?
No. The gauge transformation is what you would, I don't have a slide which says it, but it's what you would normally say. So let's think about U of A. It's going to gauge transform like a factor of G of X at the left end of the link and G dagger at X plus A at the other. So it transforms formally like it would do in lattice QCD by the endpoints of the link. So each of these fermions transforms by a separate gauge factor at both ends of the link. So in the eta case, it's the same point. So it's GX eta GX dagger. But in these cases, most of the cases, it's link forms. And so it transforms like the endpoint of the link, just as it would in QCD. So the gauge group is formally still in the group, but these guys are living in the algebra. And the reason any of this makes sense is because these are complexified. Otherwise, it would not make sense. So I'll say a bit more about that. So it's very, very tightly constructed. You have very little, everything is consistent, even though at first glance it may not be. It may look worrying, but there's really little room for maneuver. You're sort of forced by the physical requirements, by the mathematics to do things in a certain particular way. Yeah. Okay. Good. All right, so what I've written down so far is a general prescription for sticking it on the lattice, but I haven't told you what the lattice is. So you might have been thinking this is some sort of hypercubic lattice, but that can't really be true because there are 5 of these fermions. There are 5 basis vectors in the game, yet I have to be in 4 dimensions. And so you can ask, what lattice do I need? Well, it turns out, I'm not going to prove it to you here, that Q closed term it's only gauge invariant on the lattice if the sum of these basis vectors is 0. So if you just go through the variation, the Q variation, and look at what you get, you will find that you only get a closed loop on the lattice from the discretization procedure if the sum of these basis vectors is 0. So that's good because you need to be in 4 dimensions. So this has to be, you only want 4 independent basis vectors in the end. So there are 5 of them naturally in the formulation, but the sum of them is 0. It's clearly a good idea to maximize the global symmetries of the lattice theory by treating all the 5 UAs equivalently. All right, that will give you a point group symmetry of the lattice, which is S5, which is bigger than the usual rotational symmetry of a hypercubic lattice. So that's a good thing from the point of view of counterterms too. So these requirements basically select a unique lattice, which is called A4 star. All right, so there's a way to see how this works, and it relates to the continuum formulation in 5 dimensions. So suppose I'm in 5 dimensions, and then I put a nice hypercubic lattice into 5 dimensions. And let me do it in momentum space, right? Because I want to think about dimensional reduction. So I'm going to construct a hypercubic lattice in 5 dimensions, all right? Normally, when I do a dimensional reduction, I would just set one of the momenta to 0, right? I would just look at fields which are constant in one direction. But of course, I can do something else. I could always set the sum of the momenta over all 5 directions to be equal to 0 instead. So this projects also down to 4-dimensional momentum space, but it does it in a way which preserves this sort of S5 symmetry. Okay, so the result of this, if you just look by definition, if you take a hypercubic lattice and impose the constraint that the sum of the momenta are all equal to 0, you actually get what's called an A4 lattice. It's the definition of the A4 lattice. And then if I take the dual to that guy, I get the lattice in real space. So it's just the analog of the triangular lattice in 2 dimensions. I can get a triangular lattice by taking a 3-dimensional cubic lattice and then basically doing a projection, which is symmetric in the 3 basis vectors. And that gives you these lattices that appear on the, this is meant to help you out with this visualization, that appear on the surface, which are triangular lattices. So this is the same construction, just lifted up 2 dimensions. All right, so the requirements of lattice gauge invariance and Q supersymmetry essentially determine not just the form of the lattice action, but also the lattice it has to sit on. If you want to maximize the symmetries of the lattice, there's a unique lattice basically selected out, which is this A4 star lattice. It's just the generalization of the triangular lattice in 2 dimensions. So there's an A3 star lattice, which is also relevant for 3 dimensions as well, I should say. But these AN star lattices turn out to be key, and they're just sort of forced on you by the structure. Another way of thinking about these basis vectors is if you take 4-dimensional simplex, it has 5 points. If I sit at the center of the simplex and draw the vectors out to those 5 points, those are the basis vectors of A4 star, right? So you have a somewhat exotic lattice behind everything. Okay, so you've asked, various people have asked things about the lattice construction. Let me say a bit more about that now. So the fermions typically live on links and not sites, so that's very unusual from a lattice QCD perspective. To keep the supersymmetry, these complex gauge links, which carry both the gauge fields and the scalar fields of n equals 4, also have to live in the algebra like the fermions. So the measure here is not the Haar measure that it would be for QCD, it's just a flat measure. Now, normally that would break gauge invariance right away, but because U is complexified, when I look at the Jacobian that corresponds to a lattice gauge transformation, it would normally pick up, it would not normally be unity if I just had an integral over U, but because I also have an integral of U bar, I get the inverse Jacobian as well. So actually this flat measure is actually gauge invariant for complexified fields. So it's everything is okay, although you might have worried about that. At one point, we use this expansion that U has, the naive continuum limit corresponds to expanding these U fields around the unit matrix. That's how we got derivatives and hopping terms from our lattice action. If that's not true, we won't have the right naive continuum limit. So I need this expansion to be true up to gauge transformations. In QCD, this expansion is trivial because you basically are expanding e to the a. So I always get 1 plus a. This just comes because I'm in the group. But once I'm in the algebra, this is no longer guaranteed anymore. All right. Now, so what it does do is it forces you to consider gauge groups which are not SUN, but UN. Then they have a piece proportional to the unit matrix automatically inside them. And because it's complexified, you can get this I by giving a vev basically to the scalars in the trace mode direction. So what you have to do is you have to go from, it wasn't obvious at the before, but now you actually live in UN and not SUN. So that's the irrelevant gauge symmetry. That allows me to get this unit matrix basically by giving a vev to the trace mode of the scalar fields, the imaginary part of the connection in the direction of the trace. Okay, so I'm going to say more about that in a minute because this UN part is actually a problem. It leads to a sector which is difficult to control at strong coupling, and we'll end up doing something we'll have to do something to control the additional U1 modes here in the end. But I'll leave it for a moment. So anyway, this allows you to make sure you have the right kinetic operators in the theory and the right naive continuum limit. So you might worry about fermion doubling. Well, the action I just described to you describes 4 Majorana fermions in the continuum limit, which is precisely what you need for n equals 4. In fact, you can map the fermion action I told you about at the level of free field theory into a staggered fermion action, which is something that's familiar from QCD. The main problem for using staggered actions in QCD is you get 4 flavors of fermion coming out, but 4 flavors of fermion, which you don't want, typically you just want 1, but 4 flavors of fermion is exactly what you want here. All right, so it turns out that this fermion action just naturally, when you discretize it, describes exactly the right number of fermion degrees of freedom. There is no additional doubling that you have to worry about here. So fermion doubling would also be a problem from the point of view of supersymmetry, of course, because it would mess up the connection between the number of boson and fermion degrees of freedom. But sort of by construction, everything is okay. And you can sort of see it also in a different way. The boson action I wrote down has no boson doubling in it. If the thing is supersymmetric, then there will be no fermion doubling too, and then that's exactly what happens. All right. So the exact lattice symmetries, which are gauge invariance and this S5 point group symmetry in the exact Q, strongly constrain the renormalization of the theory. So you can sit down and you can power count out all the possible marginal or relevant operators which respect all of these symmetries that you can write down. And the only one that isn't already in your action, it turns out, is this guy, right? So there's a term in the action which involves the commutator of UU bar with eta, but not the actual UU bar itself. So this turns out to be a supersymmetric, gauge invariant, point group symmetric operator you can write down, which is not in the original action. And in principle, you would need to add it to the lattice action and tune its coefficient to go back to the theory you want. In fact, you can see that if U is roughly the unit matrix in the naive continuum limit, this gives rise to a mass term for fermions, which you need to tune to 0, basically. Now, actually, so far we've found it not important to tune this operator, but it's certainly something potentially you have to worry about. I'll show in a little while, in fact, that you can compute the moduli space of the lattice theory, and you can show that it's not renormalized to all orders in perturbation theory. And so this term actually can't be induced naively for that reason, because it would actually lift the moduli space. But in principle, if you don't look at the moduli space calculation, then you might worry about this operator. And so that's something we are still worrying about in principle. And now we might really have to worry about it at strong coupling. All right, but so it's kind of remarkable. You can just sit down and start writing down operators which are consistent with all the lattice symmetries that are exact. And if you power count them, so you can only do this perturbative, you power count them out, they're just basically, it's just one operator that you don't already have in the action. So it's lattice renormalizable in that sense. Okay, what are we on? Running out of time. Okay, so the structure of the lattice action is so this Q exact and Q closed piece allows some observables to be computed exactly at one loop, just like in the continuum. So you can show that, for example, if you have an operator which is invariant under Q, then the expectation value of the derivative with respect to beta here, this coupling here of this operator, just brings down a factor of Q lambda. And then and since Q always by definition invariant under Q, this is just equal to 0 by a ward identity. right? So you can show the do by d beta is 0, and that's true for any beta. So it's true. So things are Q invariant. So you can compute everything exactly at one loop. This is essentially that topological subsector I said was in the theory. You can expand this theory at a generic point in the moduli space. Again, I don't have time to do it, but it's in one of our papers. And you can show that you get at one loop, you can show, of course, you get a ratio of determinants coming from the fermions and the bosons, and they exactly cancel because of the exact supersymmetry. But because of this calculation, you can boost that one loop calculation to all orders. And you can show the moduli space is not lifted to all orders in perturbation theory, which is precisely the same as the statement in the continuum. So this one Q supersymmetry is actually a lot. It buys you much of what you'd want from the continuum theory. You can show the beta function of this theory vanishes at one loop. And this was a surprise to us when we first bumped into it. It's sort of obvious. Unlike in QCD, the Feynman graphs of this theory basically match one-to-one with those of the continuum, right? So you have lattice vertices and lattice propagators, which differ from the continuum, but the structure of the diagrams is the same. And because they're only at worst log divergent, those logs are sort of universal and common to the continuum because they come from regions of the momentum space where p is going to 0, and all of those lattice propagators become continuum-like propagators as p goes to 0. So in fact, the divergences cancel for the same reason they do in the continuum. And so this is a remarkable, strongly interacting lattice theory with vanishing beta function. So it's just kind of an amazing thing. So some more wrinkles. So you might worry that the presence of flat directions causes instabilities. Doesn't the theory run off to infinity? To handle that, we add a small Q breaking potential, which keeps the U's close to the unit matrix. And then we tune mu to 0 at the end, right? So clearly, because you have an exact symmetry when mu equals 0, any counter term associated with the Q breaking, the coupling to it is multiplicatively renormalized. So you know exactly where the continuum limit lies. It corresponds to just tuning mu to 0. And it turns out that on a torus, the Pfaffian is exactly 0 in those flat directions. So this limit as mu goes to 0 is a very benign limit. As you take mu to 0, what happens is the fermions suppress this motion down the flat directions because they have exact fermion 0 modes on torus, on the lattice torus, which give you pushes you back towards the origin in the field space. So in the continuum, often people leave those 0 modes out because they're in infinite space and they're non-normalizable. On the lattice, they're normalizable. You have to include them, but they actually do a good thing for you because they ensure, that the flat directions are actually very benign. We don't have any problems with those. This additional U1 mode I have to carry with me because I have to work in UN rather than SUN is more of a problem. It turns out this compact U1 gauge field allows for monopole condensation at strong coupling. So this is something that's well known in the lattice community, that compact U1 leads to monopoles and lattice artifacts at strong coupling. And that causes confinement and ruins the conformal phase for us. So for a long time, we struggled to try to get out to strong coupling by trying to restrict the fluctuations of this U1 mode. And so I'll show you a solution that we've just come up with recently for doing that. So what we do is, and here it is, we add an additional Q invariant operator to the action. Okay, so it just couples eta to the real part of the determinant -1. So what happens is this adds an additional potential term to the bosonic action, which keeps the determinant of U close to 1. So if you want, it takes these variables which originally were complex gauge lengths, so they were valid in GL and C, and it essentially changes the moduli space so that they live in SLNC. Okay, essentially that means it gives you a term which reduces the fluctuations in the U1 modes, but it explicitly breaks UN down to SUN. So this action now, while it's Q invariant, is no longer lattice gauge invariant under the U1 piece because the determinant is not invariant under a lattice gauge transformation anymore, right? But the SUN sector is fine, obviously. So this effectively, so we sort of able to do everything we want. We start with the formulation in UN, and then we softly break it down to SUN effectively by adding this additional Q invariant term. This guarantees, by the way, that U does have the expansion 1 plus A, which is also something we'd like, because if I'm in SLNC, then I can always write my gauge lengths as e to something, basically. And so the 1 also comes out for free with this formulation. So the final thing you would worry about here is that is there a sign problem in this theory? Can you do Monte Carlo at all with it? So you need the Pfaffian to be real positive definite when you integrate out these twisted fermions, because that's what you simulate. There's no proof, but I'm going to show you some numerical results that at least for SU2 seems to indicate that everything is fine. And I have a few thoughts as to why that might be, which I'll come to in a moment. Okay, so here's some Monte Carlo results from fairly recently, actually. This is for 4 dimensions and now U2 or SU2 gauge theory. This is the bosonic action as a function of the Hooft coupling. Let's see, these are the mu parameters, 0.1, 0.05, 0.01. And this is an 8 to the 4th lattice. And I'm setting this parameter kappa involving this new term. Kappa is the coefficient of this new term to 1. So originally, with our old work, it was set at 0, if you want. So it turns out the bosonic action lies essentially in this topological subsector I said before. So I can compute its value exactly, independent of the coupling constant. So you can show that basically the bosonic action takes this value of normalized in the way I've shown it here, takes the numerical value of 18 for the U2 gauge group. And so independent of lambda. And so what you see is that's accurately true. I mean, if you argue here 0.1, remember mu is a Q breaking term, so I expect that to be true only as mu goes to 0. And as you see, as I decrease mu, my results lie very close to 18, right? Within about 0.01 of 18. Okay, so what is that? 1 part less than 1 part in 1,000. So this is a good evidence, if you want, that we have supersymmetry all the way out to strong lambda. Right. Notice there's no sign of a phase transition. This looks quite consistent with a flat curve. If I look at the value of the determinant versus lambda, again, as I take mu to 0, which is where I want to be, I flow up towards 1. All right. So it's deviating out here at strong coupling, but it deviates in such a way that as I take mu to 0, I'm moving up towards 1. So I've now managed to produce configurations where each link has a VEV which is close to 1. Right. So I've managed to sort of project down to SUN accurately whilst conserving supersymmetry. You might say, you might want to wonder, are we really seeing the superconformal phase here? Is this a conformal theory? I just showed you there was no obvious sign of a phase transition as you went out to strong coupling, but other things you might want to check that. So here's a measurement of the string tension just from the Kreutz ratios as a function of Hooft coupling. So it's meant to be 0. Well, it's not 0, but a typical value is about 10 to the minus 3 in lattice units. So that's a very, very small string tension in lattice units. Couplings which are incredibly strong, lambda of 30 out here. So consistent with all the expected breaking of conformal invariance you would imagine for a lattice theory anyway, the string tension that we extract from a fits to Wilson loops is very small numerically and shows no sign of any kind of transition either as a function of Hooft coupling. Here I'm showing you a Ward identity for the Q symmetry just to check that's also working. And again, as mu goes to 0, it looks like the Ward identity is accurately satisfied even at strong coupling. So that's all very positive. What about the sign problem? So I'm going to write the Pfaffian of my Fermion operator as a phase times this determinant. So this is what we simulate, the quarter power of determinant MM dagger using standard RHMC techniques drawn from QCD, from lattice QCD. But if we just use this, we're insensitive to the phase. So what we do is we can measure the phase later and see whether leaving it out was a good idea. So this is 1 minus the cosine of the phase. So you want that ideally to be 0. As a function, I picked up a lambda of 10 here, so representative strong coupling, kappa of 1. And I'm showing it as a function of this Q breaking parameter mu. And so what you see is these are different lattice sizes here, different colors. It generally decreases as you decrease mu to small values. And as I increase the lattice volume, initially there's a jump from this very small lattice 2 to the 4th up to these other lattices up here, but then it seems to saturate. So we don't see an exponential increase in the sign as we increase the volume, which would be generic for a theory which had a sign problem. And in practice, if we run at small mu's down here, the VEV of the phase is 10 to the minus 3 or less, which means we really can neglect it from the point of view of doing numerical work at the moment. This is actually at first glance a bit surprising because there's no symmetry here, which is guaranteeing positivity. But you do have some freedom here. You can take this coupling kappa to infinity where you get accurately localize the theory on SU2. And then you can even localize it further because of the topological flavor of the theory to constant fields. Now, it turns out the Pfaffian of an SU2 Yang-Mills matrix model is already known to be positive definite, real positive definite. So it seems like what's happening is that the particular structure of the lattice action is allowing us to avoid the sign problem, at least for SU2, by essentially relating it to a sign problem for a matrix model, which is known to be benign. So let me move on to some I've got 5 minutes or so left. Yeah, I have not too many more slides. So
Sure.
So here's some very recent work on supersymmetric Wilson loops. So this is until basically a few months ago, we were restricted to running down here because of this U1 mode, which was causing us all kinds of problems with monopoles. So now we can go right out here. This is the square root of lambda. These are a bunch of Wilson loops on 12 to the 4th lattice, and a fairly small value of mu, but not as small as we can go, kappa of 1. So what you see is that the log of the Wilson loop is accurately varying like square root lambda as I get out to large lambda. And I should notice this is a supersymmetric Wilson loop. So it involves the scalars. Our construction naturally involves complex gauge links, or if you want sort of a supersymmetric Wilson loop when you, which naturally leads to supersymmetric Wilson loops. So this is very much in the spirit of, say, Maldaceni's calculation of the supersymmetric Wilson loop. So for us, the complexification, the fact the scalars appear up here is built in from the theory to start with. It would be harder for us to look at the ordinary Wilson loops than to look at these supersymmetric guys. And it seems like they exhibit this root lambda scaling that one expects from holography. It also emerges when you do an exact planar limit calculation. So the paper by Gross and Drucker, for example, where they compute the supersymmetric Wilson loop also is compatible with holography and also with these results. So this is the first hint that we're really seeing some interesting new non-perturbative physics coming directly from the lattice theory. We'd had agreement with perturbation theory at weak coupling before, but this is the first time we can really start saying something about strong coupling, right? And it's certainly consistent with predictions from holography. Of course, you might worry about the fact that these Wilson loops are not all on top of each other, right? If this was really a conformal field theory, then these Wilson loops should actually be independent of loop size. So it's clearly that's not the case. We have some linear scaling with the loop size. What's happening is basically that there's a piece. So our effective potential, which is governing the Wilson loops, may indeed have the non-abelian Coulomb piece we expect in the superconformal phase, but it also has a constant piece in it, right? And that constant piece needs to be subtracted out to remove this linear dependence that we're seeing. And this is true in the continuum calculation too. There is a piece coming from essentially the infinite quark mass limit, which has to be subtracted to see the non-abelian Coulomb behavior. And we're seeing it on the lattice too. All right, so our Wilson loops go like e to the minus v times t, where t is the separation, and the linear dependence we're observing is coming from this constant piece. So with the kind of limited data we have right now, the best way we can to subtract this A piece is to actually renormalize our Wilson loops by dividing by a power of the Polyakov loop. So we just measure the Polyakov loop and subtract that out. That has the same linear dependence, at least naively. And so we can try to subtract the A by just sort of forming this ratio, depending on the loop size. When I do that, it's a much improved situation. I still see the square root lambda dependence out here. But let's look at the 12 to the 4th data, it's better. So that's still there. And now here are two different loop sizes, 3 by 3 and 6 by 6. And now I'm sort of seeing them very much closer together. I've removed most of that linear dependence by taking this renormalized Wilson loop. All right, so this is what I expect for a theory with, say, a non-abelian Coulomb term, where I have, because I'm looking at these equal, so that this non-abelian Coulomb term leads to a term in the Wilson loop which goes like R over T, so R equals T, it's independent of R and T. So we're seeing Wilson loops which have the right scaling, and now also we've subtracted at least the majority of the perimeter dependence we were seeing before. the slopes here are order 1, but it's hard to compare exactly to Maldacena because he's talking about circular loops, and of course our loops are square. So the coefficient is certainly in the right order of magnitude, but I wouldn't say anything more beyond that.
So
It's actually surprising that SU2 sees such good holographic scaling, because n is 2 here. We speculate this may have something to do with the Gucci-Kawai reduction. This n equals 4 theory has an effective one loop potential for the Polyakov loop, which is 0. So it's possible that we don't have any center symmetry breaking in this theory. And so effectively by running at larger L and small, as we go to a lot, we can reduce down to a single site with an effective n, which now increases with the number of lattice points. So our effective n may actually be larger than 2 effectively. That might be one reason why seeing such reasonable results.
Do you get a good matching to perturbation theory for small lambda?
Yes, you can fit our static potential to perturbation theory. I don't have a plot, but that was done several years ago, actually, when we could only run a weak coupling, and that agrees quite well, yes. I mean, what we need to do now is a much more comprehensive job here, where we do fit the static potential more in a better way and show both limits. But this is the first time we've actually had results of strong coupling, which we can even talk about. So you need to get out to very large lambdas effectively before you're really in the strong coupling limit. You can sort of see here, you need to be you need to have lambda of order 10 before you're really in this strong coupling regime here. So there's a square root lambda. That's because of all these factors of 4 pi that are floating around, right? It's g squared over 4 pi, that's really the parameter. And so that 4 pi has to be canceled by going to pretty strong g. So we just briefly, I'll show you one other slide on with tests of holography. We've been doing a bunch of different simulations in lower dimensions. So I can take this action and reduce it down to lower dimensions and do simulations there. And so we can compare, for example, the low temperature thermodynamics of this same maximally supersymmetric large N Yang-Mills theory to results from supergravity, which are describing black DP branes. So this is a result from a very recent paper corresponding to I don't have it on here, but anyway, corresponding to D2 branes, so 3-dimensional Yang-Mills. So here are the lattices, 8 cubed to 16 cubed. The dotted line here is a supergravity prediction. The points are data for different lattice sizes. And so as you get the correspondence should hold at low temperatures, so down here. That's where supergravity should give you a good reproduction of the thermodynamics of the supersymmetric theory, and you can sort of see the data is coming down to lie on it. There's no fitting here. This is all the normalizations are fixed by supergravity, so you either get it or you don't get it. And so this is the high temperature limit, and so you're dropping off the high temperature curve and coming down onto the low temperature supergravity prediction, and arguably here you're already on it. It's extremely hard to get further lower in temperature because of various other kinds of instabilities that occur at finite temperature. But everything is consistent with holography, at least at this point. All right, so let me just wrap up because I think I've had my hour a little over. So I told you there's a class of supersymmetric theory that can be discretized, preserving some SUSY, and basically focused exclusively on n equals 4, but there are other examples in lower dimensions, many other examples. They all use the same technology, but they differ in details. The lattice symmetry strongly constrain the quantum effective action. The moduli space survives quantum correction. And only a single marginal operator may be needed to tune to restore all the SUSYs in the continuum limit. Lattice simulations of n equals 4 show you a single deconfined phase at all couplings. I don't think that will change. If we go to lambda of 100, I don't think we'll see any difference. I'm pretty confident. There are hints of the right holographic scaling and good agreement with leading black hole thermodynamics at large N. That's what the slide I just showed you. Of course, there's a lot more we could do. We'd like to do a much better calculation of Wilson loops so that we can really get a good handle on the full effective static walk potential and really make an agreement both with Maldacena and Gross and Drucker and think about how we would do circular Wilson loops in this language, but also make the connection down to weak coupling too. There are lots of other things we'd like to go after, like measuring the Konishi anomalous dimension, tests of S-duality by going out on the Coulomb branch. We know how to do that in principle. It's just it has to be done. It's non-trivial. There are things like the 3/4 problem, looking at the thermodynamics of n equals 4. That's something we're actually looking at right now because it's an easy thing for us to do at this point. We need, of course, to check for restoration of full supersymmetry and continuum limit. Weak coupling, there's no problem at all, but it's strong coupling where you can't necessarily trust power counting. You have to be, check other things to make sure that you restore all the supersymmetries. And if you don't do that correctly, you won't get the right answers for things like S-duality either. So this really needs to be done ahead of some of these other things, really. I haven't had time to tell you about it, but you can generalize these lattice constructions to quiver gauge theories, and you can even target certain super QCD-like theories. Not super QCD in 4 dimensions, unfortunately, only in 2 or 3 dimensions. I don't have time to explain, but it turns out that super QCD, while you can handle it with a similar set of technologies, it's restricted to dimensions less than 4, effectively, at least as far as we understand it right now. Okay, thank you. Sorry for going over a few minutes.
All right, so thank you very much, Simon, for this was very interesting. So are there questions or comments? Okay, I see in the chat.
Oh, yeah.
A question by Jun Baoru. What can we obtain if we only use strong coupling expansion without numerical computations?
I think that's an open question. I know Paul Damgaard in his postdoc a few years ago tried to formulate a strong coupling expansion here. It's a little tricky, apparently, because in a normal strong coupling expansion, you expand in something like the quark mass or something like that. So you have more than one parameter in the problem. In this case, we have only one parameter, or at least, which is just the coupling lambda. And so it's harder to formulate a convergent strong coupling expansion. I think that's what essentially Paul told me at the time. So it has not been looked at very extensively, and that was only in the days before we had this new term involving the link determinant, which gives you another parameter. So it might be possible to do something now which was not possible in the past. I think it would be kind of interesting to do. I mean, so I'd encourage anyone who's interested to try thinking about a strong coupling expansion and seeing how much you can get out of it, because I think it's a natural thing to do once you have a lattice theory. Absolutely. I mean, it was Wilson's original motivation was to formulate a strong coupling expansion, right? When he formulated lattice QCD in the first place. So I think it would be nice here. I know it was tried briefly and did not seem to work in the old days, but I think it's possible now. It might be worth revisiting that.
Okay, so more questions? Remember to unmute if you want to ask.
One question, can you deform the theory once you have the lattice formulation to get less supersymmetries or something?
Well, it's tricky. You kind of have less to start with, right? The focus is mostly on restoring those guys. But the question is, are there other ways that are compatible with the exact Q symmetry that you could deform the theory? Other than the theory you're writing down already has only one supercharge, right? So in some sense, it's already deformed, and you're hoping to regain the rest. The question is, can you put something in place which is Q exact, which will stop you regaining full n equals 4, right? I guess that's what you're saying.
Yeah.
Possibly. I think the truth is it hasn't really been thought about carefully. If you do naive things, you'll just break Q supersymmetry, and then everything's off. Everything is broken at that point. You could. So here's one suggestion. This one operator that I told you about that in principle you should account for in the action. It's not in the original classical lattice action, but you could potentially induce it through quantum corrections. If you played with the coefficient of that, you might be able to build a theory with quark which has less supersymmetry by building in certain fermion masses. And that might be possible, but I don't know what that would correspond to in terms of the original you know, n equals 1, n equals 2 supersymmetry, which is what you're actually probably interested in, right? I don't see an easy path to that, but it's not impossible. I mean, one of both the advantages and the disadvantages of this lattice construction is it's very tight. There's very little you can do. You know, the lattice is constrained by all the symmetries. The counterterm structure is very constrained by the symmetries. So you don't have too much freedom. So I think it's not impossible, but it's not easy to do, to do what you want.
Yeah, sure.
I mean, it'd be very super interesting to do like n equals 2 somehow.
Sure.
Yeah. By the way, you can't formulate n equals 2 this way, sadly, because the twisting procedure doesn't work. And you end up with still, I mean, if you think about the usual topologically twisted form of n equals 2, it still has spinor indices in it, right? So you don't remove all the spinor indices, and that seems to be a crucial constraint in these lattice constructions.
Thank you.
More questions? Okay, so I have another one, if I may.
Sure.
So you started with a 5-dimensional lattice, which involves some type of dimensional reduction, but you didn't talk about the size of the 5th dimension of the lattice. So is there another parameter here related to the S1 that you use for the topological simulation?
When in the lattice construction I was sort of using as a motivator for the A4 star, I mean, I was in like a 5-dimensional cubic torus.
So the size of this lattice in lattice units in the 5th dimension plays a role. You have to tune it. You have to do something.
No, I mean, I mean, none of that was strictly gauge invariant, right? I mean, it gave you this argument of momentum space you should be sort of suspicious of as immediately when it comes to, you know, if you have a lattice gauge theory, you don't have a well-defined notion of momentum space, right? So it was really an argument at the free limit. So I don't know. So the construction, I mean, it's important to realize that you don't require that 5-dimensional picture to write down the lattice action. It's just a motivator for why you end up with this structure, which looks like it wants to live in 5 dimensions. It lives in 4 dimensions. It's just on this funny lattice with 5 basis vectors. And in the continuum, you can imagine how you would get there by doing a dimensional reduction from 5D, but it's not like you actually construct the lattice theory in 5D and then drop it down to 2D by a particular operation. That's not what's happening. All right. So I would say that the picture from 5 dimensions is a motivation, but it's not part of a real construction. In fact, this theory is not gauge invariant in 5 dimensions. That's what I said in some sense. The basis vectors have to sum to 0, right? If I write it down on a cubic lattice in 5 dimensions, the Q closed term is not gauge invariant. Only when I say that no, these basis vectors are all linearly dependent and the sum of them is 0, that's the only time in which it becomes gauge invariant again. So in that sense, it's not really a dimensional reduction. It's a sort of a constraint on the basis vectors. I don't know whether that's helpful. So the arguments from 5D are appropriate for discussing the continuum version of the theory. And they motivate why the lattice theory comes out with in the language that it does, in terms of what look like 5-dimensional variables, but they're really just variables appropriate to a lattice that lives naturally in 4 dimensions, right? The A4 star. So it's perhaps a little confusing. Yeah.
Okay.
Yeah. So you shouldn't think of this lattice as coming from a 5-dimensional lattice. I think it's a motivation for understanding why A4 star is important, but you can't do that in a gauge invariant way. There's no gauge invariant construction which allows you to go to A4 star from some 5-dimensional lattice. That's the right way of thinking about it.
Okay. Any more questions? All right. So if not, I would like to thank Simon again for this nice talk. So I will clap. And
Okay.
I'll stop the recording now.
Now, sharing here. Thanks. All right.